The second part of Lab 3 discusses parameters of spectrograms and basic reading of spectrogram displays that we're going to use in analysis of speech. So for question 4, the first two questions contrast two statements about a spectrogram with a smaller bandwidth. Bandwidth is a term that is used for the range of frequencies in some sort of band in an analysis of speech. So if the bandwidth is smaller, that kind of translates mentally to a narrow range of frequencies. In a spectrum visualization of what a resonator or a filter does, if we think of something that resonates and enhances as something that has a peak, where that peak amplifies amplitude, versus down in the troughs, reducing, subtracting from amplitude. The bandwidth visually would be kind of how wide is that peak. So if we make those sort of peaks narrow, then a narrower range of frequencies are going to be, say, increased if they're near the peak, and everything that's away from that narrow range of frequencies is going to be decreased. So what will happen generally then with a smaller bandwidth is we'll get a more precise image of what frequencies are. So second statement would be true, first statement would be false. Dynamic range is the amplitude range displayed in the spectrogram. The spectrogram display uses a grayscale to show amplitude. At some point, you got to kind of pick a maximum value for amplitude, a point where something is going to just be solid black and isn't going to get any darker. And on the other end, an amplitude where the amplitude is low enough that you're just not going to bother to show that as gray. It's going to be white at that amplitude or lower. So the idea then with the dynamic range is we can have it be larger or smaller. The smaller we make the dynamic range, then the cutoff from what we show as black versus what we show as white is narrower. Let's see, a larger dynamic range, same idea, but a lower amplitude before we cut things off as white, a higher amplitude before we sort of give up on showing amplitude definitions, and just show black. So the larger dynamic range will show more noise, and the smaller dynamic range will cut more noise out. Similarly, if we were interested in kind of differences between very loud sounds, larger dynamic range might show some of those differences. A smaller dynamic range would hide them. Question 5 is a little bit of review of our displays of sound, and there is a displays of sound handout that's posted on As You Learn as well. So we had 3 types of sound displays here: the waveform, the spectrum, and the spectrogram. The waveform, we had pressure values that we recorded at a microphone over time. The spectrum, we were interested in looking at frequency values, and we looked at them with respect to their amplitude. And then in the spectrogram, we put those 2 dimensions of sound, time and frequency that we're interested in together. So we have time across the bottom, frequency up the side, where our third kind of unlabeled dimension is darkness. So louder things being dark, quieter things being not so dark. And actually, to use this spectrogram as an example from the previous question 4, if we were to take that dynamic range down a little bit, we might be able to get rid of some of this gray on the edges and have it show as white and better highlight kind of our darkest fuzzy caterpillar areas that are going to end up being reflective of various characteristics of speech production. In terms of our basic sound types, we had periodic sounds, which can be either simple or complex. But when you get into the real world, when you get away from weird things like a tuning fork or things like pure tones generated by a computer, pretty much everything is going to be a complex periodic sound. It's going to have more than just the one frequency of a periodic sound in it. Other sounds are aperiodic, and there were 2 types of those: noises that go on for a while, transients that are very brief and stop. And then a kind of 4th sound, not sound, basically being silent. Each of these types of sound is relevant to our analysis of speech production. The cue for periodic sounds are these vertical stripes here. And also, to some extent, these fuzzy caterpillars, these frequency regions where the sound appears to be louder. Those 2 things are going to be reflective of basically our speech sound source and the vocal tract as a resonator. So we've also got some periodic here, some periodic here, and some periodic here. And we are supposed to find 4, and I've got 4, so I'm in good shape. Transients and noises potentially look similar because they're not periodic, but transients are not periodic because they're very brief sounds that happen once. Those are going to show as vertical stripes on the spectrogram. So there's a transient there. There's a transient there. Here's another transient here. And I'm supposed to find 4 of them. There's another little one right there before that periodic sound starts out. Last but not least, we've got 3 noises. The really obvious noise is this one. Its structure is pretty different from the periodic sound next to it. It does have some louder amplitude areas that I might want to draw one of these kind of fuzzy caterpillar circles over, but they tend to be bigger blobs. It also might look a little bit like it's got that vertical striation look to it, but it's not nearly as regular as our properly periodic sounds. There is a second bit of noise in here after the transient, and there's, I guess, a third really little bit of noise because I don't see another one in here after that transient, and that would give me 3 noise regions. And then last but not least, I've got silence. Well, silence is basically very little amplitude, and so that's going to be these white areas in here. And that gives me 4 of them, and then I guess the speech sort of ends, and I have a little bit more silence at the end that shows up in my image, and I'm supposed to find 5, so I guess I'm going to call those my 5 regions of silence. In the spectrogram display, again, we have time across the bottom. So the different bits of speech that we're going to be looking at are going to have a somewhat similar look over chunks of time. So I'm sort of visualizing the content in this spectrogram as these sort of big rectangles of what's going on across the frequency spectrum at any particular time. And we'll return to doing a fair bit more than that in the third unit on resonance.